Good morning, afternoon, and evening, everyone. Welcome to today's webinar. My name is Kalyan Sundar, and I'm VP and General Manager of the 5G Edge-to-Core group at Keysight Technologies. We have some great content prepared for you today, which will be followed by a question and answer session. Please feel free to submit those questions at any time during the presentation. We also ask that you take the time to answer a brief survey and let us know how you're doing or tell us what your business challenges are. Completing the survey helps us develop future webinars for you. Now on to the presentation. Today, we will talk about the ORAN group that defines the specifications, the reference architecture, and the interfaces between the various subcomponents that form the ORAN. This group is called the ORAN Alliance. Next, we will talk about the ORAN architecture itself, where we will examine in detail the various subcomponents that form ORAN, the interfaces between them. Finally, we will talk about some practical challenges as this architecture is taking shape and getting into early deployments. ORAN is an operator-led alliance which was formed in February 2018 by 5 global operators: AT&T, China Mobile, Deutsche Telekom, NTT Docomo, and Orange. The purpose of this operator-led alliance was to define the next generation RAN architecture as well as specify the interfaces and interconnects between the various subcomponents of ORAN. ORAN was formed as a merger between XRAN group that had been in existence for a couple of years before that and the CRAN alliance, whose purpose was to define virtualized RANs. If you take a look at the members, you can see now it has grown from 5 to 24 global operators. Here is a list of who's who on the right side of the screen. It has also grown to 148 other contributors, which are NEMs and other parts of the ecosystem of ORAN, which you will see in the next slide. This group has an entire ecosystem of other contributors that vary from traditional NEMs that we are aware of, as well as various other members of the ecosystem, including chipset manufacturers, companies that build stacks, companies that build radio elements, so on and so forth. Keysight is a member of ORAN from the very beginning, and we have been focused on the conformance and interoperability testing between the various components. This group now stands strong in addition to the 24 operators at a total of 148. The desire for wireless operators to move their networks from physical purpose-built hardware to virtual and cloud-based software implementations of the various network elements has been there from the 4G days. For core networks, this is closer to reality. ORAN Group is striving to do the same for the RAN side of the network. They do it by specifying the different disaggregated or discrete components of the RAN and the interfaces or interconnectivities between them through standardized interfaces. This would allow them to be hosted on white box hardware as opposed to purpose-built hardware that were prevalent in the past. This opens the door for operators to a plethora of vendors that are best in breed in what they do. Each subcomponent of the ORAN could come from a different vendor, and even pieces within the subcomponent could be from different vendors. Now, before we move into that in more detail, I want to address the different groups, and there is some confusing terminology there. Open RAN should not be confused, as an example, with the ORAN. ORAN, as we talked about, is the group that specifies and defines the RAN infrastructure. In some cases, it works with the 3GPP group to refine some of the specifications even further, like the interfaces between the E node B and G node B, called the X2 interface. It does this embracing the principles of openness as well as intelligence. We'll talk about that in a slide. Open RAN is different from that. Open RAN is actually a project group that's part of the telecom infrastructure project. And the main objective of this group is interoperability between the various disaggregated RAN components. Again, they're striving to build the same using open interfaces. Starting this February, these groups will work together. In fact, there is a contract between the Open RAN and ORAN Alliance to reuse some of the specifications defined by the ORAN by Open RAN group. This allows the Open RAN group to progress further with interoperability testing. Now there is yet another group here, which is the Open Networking Foundation, whose purpose is to build open source software. Now they're working closely from January of this year with the ORAN Alliance, so they can actually have open source implementations that can be verified using the ORAN components and also conforming to the specifications defined by the ORAN Alliance. Recently, there is also an Open RAN policy coalition that was formed. This is as recent as May. And the purpose of this group is to be an advocate for government policy that can drive more Open RAN adoption. ORAN Alliance is built on two core principles. One, openness, and second, intelligence. When you think of service agility or cloud scale economics, you're talking about virtualization of services into network functions, NFVs, and also utilizing the large cloud scale operators that give you economies of scale by providing larger components at lower cost. Now, service agility is how fast can you actually take a service and get it into production. Much easier with software, much faster with software than hardware, where it takes a lot of time in ensuring that the hardware is thoroughly tested in the lab with various other components before it goes into the field. In addition to this, you bring in the small vendors into the equation. When you think of small vendors, think of it this way. Operator now has an opportunity to work directly with RF contract manufacturers. They also can work with companies that specialize in GPUs, FPGAs, virtual cloud infrastructure providers, rather than just working with few companies that used to make the big RAN component. This allows them to mix and match the various components and ensure that there is a partnership between best-of-breed vendors in these areas to create a very powerful and unique solution. This brings up two things. One is makes the ecosystem very competitive and to the operator's advantage. In addition, it also embraces open source software. As I mentioned earlier, ONF is already working with the ORAN Alliance to use their specifications to create open source software for many of these components. The second principle, which is intelligence, stems from the fact that 5G is going to generate a lot of data. Humanly, this is going to be very difficult for somebody to analyze this data and make some corrections in the network. Whether it's adding capacity, looking at employing certain services in certain regions, so on and so forth. So you're going to use more and more of AI and machine learning models to collect this data, create some and do some analysis based on deep learning and feed it back to the network. All of this in an automated fashion. That's what we mean by self-driving networks. This is expected to reduce the OpEx quite extensively. Studies today show that there should be a 40 to 50% reduction in OpEx costs for the network service providers. This slide shows the O-RAN architecture on the left, which we will examine in more detail in a few slides. And on the right, you have the associated O-RAN Alliance work groups that specify the various components and interconnects of this architecture that you see on the left side. Now, Keysight is participating in all of these work groups, and very specifically I want to point out in work group 4, Keysight is the editor of the O-RAN fronthaul conformance and interop test specification. Now we'll talk about the O-RAN architecture and how the various work groups in O-RAN Alliance specify the various components of this architecture as well as their interconnects. We will start with work group 1, which defines the overall use cases in the architecture. Then you go to work group 2, which defines the RAN intelligent controller. The RAN intelligent controller is broken into two pieces. One is the non-real-time aspect, which is what this work group is responsible for. In this case, we are talking about policy information, configuration of the non-real-time pieces, and also sending some of the AI models over to the near real-time aspects of the RAN intelligent controller. It does this over an interface called A1, which this group is responsible for. Moving to the near real-time aspects of the RAN intelligent controller, this is where the information is assimilated as to the control and optimization of the RAN elements and sent over from this intelligent controller over to the different pieces of the O-RAN, including the OCU, which is the central unit, and the ODU, which is the distributed unit. Next, you have work group 4, which is responsible for defining the open fronthaul interface. This is the interface between the radio side and the what we call the DU, which is the distributed unit. And the interface between this is going to be Ethernet. Typically, eCPRI is the interface, but you also have CPRI as well as IEEE 1914 involved here. So on the other side of the RU, you're talking RF going out to the user equipment. So that's the end of your O-RAN or RAN. And on the side towards the core is all Ethernet. So this is a very, very important interface that is being defined. Next, you have work group 5, which is the connection point between the distributed unit of the RAN and the central unit of the RAN. Now, the central unit itself is split into two. You can implement it as one central unit, or you can actually have a control part and a user part. And the reason it's done this way is it allows flexibility for the operators to take, let's say, the user part and move it closer to the edge where you can deploy some mobile edge computing services. And similarly, on the control side, it allows them to actually host this more in the cloud. Interface between the control plane and the user plane in the CU is E1 interface. So this group is actually responsible for a wide variety of interfaces, all related to the CU, whether it's the F1 coming from the DU towards the CU, or it's the E1 between the CU control part and the user part, or the X2 interfaces between the 5G RAN and the eNode B from 4G side. Next, you get into the cloudification and orchestration aspects, which allow you to take many of these components and virtualize and host it on cloud. So this is where you are looking at taking these entities, making it NFV, and hosting it as VNFs on the cloud. Workgroup 7 talks about the separation of the physical aspects from the virtual aspects, allowing you to create white box hardware. Similarly, Workgroup 8 looks at the reference design for the stacks, what goes into the CU/DU specifically, and how it works with the 3GPP or builds on top of the 3GPP specifications. And finally, you have Workgroup 9, which is looking at the Ethernet interfaces that form the backbone for many of these, including the mid-haul and the backhaul networks. I'm going to leave this slide with one additional thing, which is the test and integration focus group, which has the responsibility of defining the overall approach for testing and integration. We'll talk about this in the next slide. The test and integration focus group, TIFG, has come up with OTIC, or the ORAN Test Integration Center, which will be an entity that certifies or gives you a formal certification, compliance certification of your ORAN component, whether it's a network gear or a subcomponent that goes within it. The host for this has to be an ORAN member, that is an operator. It has to be a non-vendor ORAN contributor, could be a third-party authorized test laboratory. So there's already talks about doing this in multiple parts of the world. It's going to take some time, but there's already some plans going on as to where these OTIC centers would be and when you could be having these testing. Now, one thing it does is it allows all these vendors to actually test to a specific set of test cases and ensure there is compliance to that. Before we take a look at the ORAN architecture for 5G, let's start with the evolution of the front haul from its 4G days. As we go into 5G, it'll be evident that the front haul is much more challenging, and as a result, this will lead us to looking at the splits defined by 3GPP. On the left of this picture, you will see the stack, starting with the RF, going all the way up to the PDCP. On the right, you actually start seeing the mapping, starting with 4G and moving all the way to ORAN. So let's examine this in more detail. With 4G LTE, you had a centralized baseband unit connected to a remote radio head through the CIPRA interface. Because of the total bandwidth and fewer antennas involved, the data rate between the BBU and RRH was sufficient for LTE. With 5G, there was a lot more data that needed to be passed back and forth because of higher bandwidths in 5G and also advent of more antenna ports through massive MIMO. So two solutions came into existence. First one is the high-level split, which is a two-box solution where you move most of the processing to the edge. And the interface between the DU plus RU in that case, which is in the edge, to the centralized unit is the F1 interface. Alternatively, you have the LLS, which is the low-level split, where you're moving more to the center and keeping the antenna to the edge. This was what XRAN was defining. Now, if you note, these are the two work groups that we talked about, work group 5 and work group 4, eventually evolved from this. with O-RAN taking over, we are looking at three distinct components. The ORU, or the radio unit, which is at the edge, and then you have the DU that's in the middle, which is going to do some of the processing, and then you have the centralized unit. So you have both the high-level split, which is the F1 interface, and the low-level split, which is going to be an eCPRI interface, which is the front haul. Now, with O-RAN, these interfaces became more standardized. So you could have different vendors bring in their CUs and DUs or RUs. As a result, these components are much more interoperable. These protocols are clearly defined. Again, an undertaking from O-RAN, work group 4 and 5. 5 defines the F1, 4 defines the front haul. And all these are tested by Keysight. I'm going to get into the splits more in the next slide. With 5G, we are going to see a bandwidth explosion. And here are some numbers. On the left side, you see the LTE channels, typically 10 or 20 megahertz. And if you go, let's say we take a CPRI interface, which is between the BBU and the remote radio head, you're looking at line rates anywhere between 600 megabits per second to 10 gigabits per second, depending on the bandwidth, whether it's 10 or 20, how many MIMO channels you have. In this case, we are showing 10 megahertz gets you, with one channel, you're going to have 614 megabits per second. With 8 of those, you're going to require about 5 gigabits. And then with 20 megahertz channels, you're going to require about 10 gigabits. Very doable, and that's why CPRI was prominent between the BBU and the radio head in the LTE days. As you move to 5G, the bandwidth itself is 100 megahertz in many cases, or even beyond. And you're looking at, let's say, 8 antennas. You're starting to look at 28 gigabits per second line rate that is required between the radio unit and the baseband unit. And if you continue to increase, which is the intent, where the bandwidths go higher, 100 to 200 to 400, let's say 500 megahertz is the example we have here, you're starting to look at 140 gigabits per second. And, with a massive MIMO introduction, you are talking about something like 2 terabits per second. So to have 2 terabits worth of traffic over CPRI is just untenable, which is the reason why we have splits. In this slide, we will talk about the functional splits and how it relates to the O-RAN architecture. The top part of the picture has the O-RAN architecture with its various subcomponents. The ORUs, ODUs, OCUs connected to the core network. The bottom part of the slide, you see the various stack layers like PDCP, RLC, MAC, and physical layer. The splits define where each of these stack layers are housed in the top picture. For example, should the PDCP be in the CU or the PDCP be in the DU? That's what the splits is going to determine. So before we go to that, we need to first understand a couple of factors that play a big part here. One is latency, and second is the distance restrictions that you have. So let's start with the RUs. So RUs is typically where the antennas are, and the connectivity between the RUs and DUs is commonly known as the front haul interface. Typically, the distance between the two is about 10 kilometers. It's also based on some very low latency requirement for transporting packets back and forth between these two. You're looking at 100 microseconds type latency requirements between the DUs and the RUs. you see that we have chosen an eCPRI interface here. And the reason eCPRI is chosen over a CPRI interface is in eCPRI, you just have to send user data. You don't have to send if there is no user data between the DUs and RUs. That greatly reduces the bandwidth requirements between these two. Now, we'll talk about a few options before we zero in on the option that you see there on top, which is option 7.2. You could move all of the physical layer functionality into the RUs, in which case you will actually have a fairly complex RU here, which has the antennas as well as all the functionality moving to the edge. Now the bandwidth requirements go down tremendously. You're now talking only about 3 to 4 gigabits of bandwidth requirements between the DU and the RU, but you're also talking about a very complex RU that's sitting on the edge. Now the flip side of that is you go with let's say an option 8, which means you are putting all the physical layer functionality into the DUs and just keeping the antennas at the edge, which is the RUs. This is similar to what we saw in LTE architecture, and you had the connectivity through a CPRI interface in that case. But with 5G, we just saw in the previous slide, the bandwidth requirements just explode. So in this case, even for a nominal scenario, you're looking at 200 to 300 gigabits of transport required between the DUs and RUs. That's untenable, which is why we talk about the 7.2, which is a very optimal split between the DUs and RUs. So what happens here is the PHY is broken into two, low PHY and high PHY. The low PHY stays in the RUs and the high PHY stays in the DUs. As a result, the bandwidth required on this front haul interface is about 20 gigabits for 100 megahertz bandwidth with some MIMO capabilities involved. Now, as we move from the DUs to the CU, you're looking at typically an upper layer split where it's called option 2 split. And where this is split is the processor intensive functionality moves into the CU. The remaining part of the stack stays in the DU. So the MAC and RLC along with the Hi-Fi stay in the DU, and this is the option 2 split, also split with the F1 interface. There is two pieces here. One is split at the control level where you have an interface between the DU and the CU, which is the F1 interface called F1C, where you are sending control information, and then F1U, which goes into CU, another part of the CU. Now the CU itself can be broken into two, a CU UP and a CU CP. But this is the F1 interface, and typically the data requirements are about 100 gigabits between the DU to the CU. You're also talking about a little bit higher latency requirement here. You're talking more like in the millisecond range. And the distance here between the CU and the DUs, and one CU supports many DUs by the way, the distance requirements is about 80 kilometers. So that's the option 2 and called the F1 interface. We will talk about both the option 2 and 7.2 in much more detail in the next slides. And finally, you have the backhaul interface, which is the connection point between the CU to either the 4G network in case of NSA or 5G core network in case of SA. The requirement there is, you got a lot more distance, and it's more like 200 kilometers range between a CU and the 5G core. And you're also talking about much less stringent latency requirements, more in the order of 40 milliseconds. As we migrate towards more open front haul interfaces, it comes with its own challenges because now you do have to unit test a lot more pieces in addition to doing a peer emulation of the ODUs or ORUs towards each other. So there are challenges there. In addition, we are looking at conformance testing in addition to interoperability and performance testing of these components. The new functional splits that we talked about in the previous slide, 7.2 or option 2 or the high level split, are going to require newer test capabilities. Because what you test for OCU is different from what you test for ODU and what you test for ORU. This is also an interesting relationship going on between an RF domain and a digital domain where timing becomes very critical. It's also very protocol intensive in terms of setting up connectivity, passing on control and user data, and also looking at lots of data going back into the core network in the backhaul. Finally, there is a interesting relationship between the O-RAN Alliance and 3GPP. 3GPP defines a lot of the standards and continues to, but O-RAN is also spearheading some of the specifications and also refining some other specifications like the X2 interface. Now we'll take a look at the O-RAN architecture. In this section, we will look at the front haul interface as well as the F1 interface, which is a high level split. This picture shows you the entire 5G network from the edge to core. You see the UEs on the left side talking to this purple box over RF. The purple box is your O-RAN, divided into ORU, ODU, OCU, as well as the RAN intelligent controller. The blue box here is the core network. It could be 4G or 5G. If it's 5G, it's going to connect over N1, N2, N3. If it's 4G, it's going to connect over the S1 interface. And then the core network is connected to the internet over the SGI or N6 interface, depending on whether it's 4G or 5G. The ORU is the radio unit, as we talked about. It hosts the RF functions and some part of the PHY. Since we are talking about option 7.2, it's going to host pieces of the low PHY at the ORU. This is not virtualized. Typically, it's a physical purpose-built hardware that we're talking about, which takes the IQ samples coming from the ODU and converts it over to RF. Next is the ODU. The ODU hosts the other pieces of the PHY, call it the high PHY, as well as layer 2 like MAC, RLC. The ODU can be hosted either as on purpose-built hardware, or it could be hosted with accelerators on GPUs. It could be hosted on cloud infrastructure as well. So ODU has a lot of possibilities. And then comes the OCU, which hosts the PDCP layer for data as well as the RRC for the control. Now, this is typically going to be virtual. It could be hosted alongside the core network, 5G core network, in the cloud. The OCU could also be split into the user plane and control plane, where the control plane has more potential to be hosted alongside the 5G core network, and the user plane is going to come more towards the edge, especially for mobile edge computing type applications. As we look at the front haul interface, you are defining the control user synchronization and management planes, the C, U, S, and M planes. And you can see the overall relationship of that in the grand scheme of the rest of the O-RAN components. So the front haul itself uses an optical link, which is basically just an Ethernet transport, typically a 25 gig or multiple 25 gig links. It could be 100 gig as well. And these links carry the user data that goes between the DU and the RU, the control that sets up the user data, The synchronization, highly important to make sure that the DUs and the RUs are synchronized. You use protocols like PTP for that. And very importantly, the management plane, which is the M plane. The management plane sets up the whole thing between the DUs and the RUs using netconf and multiple Yang models. This is how the configuration information is exchanged between the DUs and the RUs. It's also been a very challenging task because there are many things that are left to user interpretation, deemed as optional, and when DUs and RUs try to interop, this is an area that's been an interesting challenge, especially in the early phases of deployment. In this slide, we will look at how the protocols, starting all the way from the Ethernet, UDP, and so on, map to the eCPRI and the ORAN. So if you look at it, the eCPRI rides on top of Ethernet, and the ORAN protocols, mainly the CU, S-plane, and M-plane, are on top of that. And you can see all the protocols here and how they are mapped. Now, in this detailed slide of the fronthaul architecture, we are looking at the various building blocks. What you see here is the split between ODU and ORU is your 7.2x split. Now, there are some boxes that are shaded in dark blue, just showing that these are mandatory. Not all ORUs have this, depending on the categories. There's also category A ORU versus category B, where in category A ORU, the precoding is actually done in the ODU, and the digital and analog beamforming are optional. In category B, the precoding is done by the radio unit. Now, there's a big difference between 7.2 X split here, which is about 20 gigabits of transport required between the ODU and ORU for, let's say, a 6040, 64R, 100 megahertz channel. If you moved up and said, let's say, we want to do 7.3 split instead of 7.2, then the division between the ODU and ORU would be at between the scrambling and the modulation. Where the scrambling is done in the ODU, everything below moves to the ORU. So here, since majority of the functions are being handled in the ORU, the bandwidth requirements come down quite dramatically. It will be more like 4 gigabits per second or so in this case. But you're also moving a lot of the processing to the ORU in that particular situation. That's the 7.3 split. Now you can go for a 7.1 split where your beamforming is done in the ODU. So right until the point of digital beamforming is going to be done in the ODU, which means only IFFT and below will be done in the ORU. In this case, you're increasing the bandwidth quite tremendously. The requirement for the same scenario would be more like 140 gigabits per second. So you can see just by placing these different blocks in ODU or ORU, the requirement of bandwidth between the ODU and ORU varies quite tremendously. Next, I want to talk about the OCU and the mid-haul architecture. On the left of this picture, you see the OCU connected to either the 5G core or the 4G core, depending on whether it's SA or an SA scenario. And on the right side, the OCU is connected to ODU over the F1 interface, which is the high-level split option 2. You can see that the ODU is connected to the OCU independently over the user and the control planes, because the OCU itself can be split into a CP and a UP, and they can be hosted on completely different machines. The CP could be hosted more with the core. It could be virtual or containerized in a cloud environment, while the UP typically is going to stay more closer to the edge, especially for mech scenarios. And the connectivity between the CP and the UP is through the E1 interface. So in essence, what's happened is some of the resource-heavy features, especially the PDCP, which does ciphering and integrity protection, as well as reordering at the NR level, they are moved into the OCU. That's where the PDCP resides. As well as the PDCP determines the ratio of what traffic goes to LTE and what traffic comes into NR, especially in the NSA type environment. And there are many, many combinations there which make it pretty intensive in terms of how these packets in the end, on the downlink, let's say, reach the user, and the uplink, how they're distributed to the 4G or the 5G networks. This is a summary slide for why we go with option 72X. We have covered most of these points, but just to highlight a few here. With 72X, you're only transmitting user plane data, which greatly reduces the total transport bandwidth required on the front haul. We also looked at what happens if you split differently, whether it's a split 8, which requires a lot more data, or a split 7-1, which also requires a lot more data to be transmitted, versus splitting at a higher level where you're looking at 7-3 or so on. In that case, you're actually going to have a lot more difficulty in interop because there's more parameters to be defined. So 72X is an optimal one where there are fewer parameters to define. It's also easier to upgrade because you're going to upgrade the functionality in the ODU without a lot of changes to the RU, which is typically more hardware intensive. So far, we've looked at the O-RAN alliance, which defines the reference architecture and the specifications, and the O-RAN architecture in a bit of detail on the front haul and the mid haul side. Now let's take a look at what are the practical challenges that we are facing as O-RAN goes from specs to implementation and interoperability between the various components. As O-RAN moves from architecture to implementation and deployment, we see the following general challenges. One, with more vendors, there is going to be more interoperability challenges, especially in the early days of the specifications. It's not sufficient to just interop with other components, but it's also necessary for these components to be conformant to the specifications. Performance also forms a very major part of this because we are trying to control the amount of bandwidth between the ODUs and the ORUs. The second part here is the ownership model. Is it the service provider who is responsible overall, or all these disaggregated components are responsible when a problem comes up? That's going to be a challenge. And the market shift, especially in the O-RAN area, where you're going from purpose-built hardware to software and cloud, and introducing various other components along the way, is going to be challenging. Now, this challenge has already been resolved in the move to data centers as well as the shift to cloud in general, but it will be a new challenge that the RAN faces in this particular case. Finally, the test complexity. You have more parts, more components, more interfaces. There is going to be more complexity as a result. And to add to that, you also have the splits where you are moving functionality, especially of the PHY, between the ODUs and ORUs. It's going to be a challenge as well. In addition to the bearer split function that we talked about, where in some cases you're going to be routing more traffic to the LTE and in some cases more traffic to the 5G NR network. Let's talk about some of the specific challenges we have seen so far based on our experience with customer interactions. One of the big ones is, what is the DUT in this case? There are very few engineers who are adept at both RF and Ethernet. And this has posed a lot of challenges as you move between the analog and the digital domain. The exposure to the specs and the interpretation of the specs is also not something that's uniform across the board. So there have been challenges in how we've taken the interpretation and implemented some of these components. To get into specifics of ORU vendors, there's a lot of timing issues we've seen. The M plane itself has been either very preliminary or in some cases absent. So you have to bypass the M plane in many cases. There's also the whole synchronization where the challenges are in terms of the clocking and the synchronization between the two components, the ORU and the ODU in this case. From an ODU perspective, the vendors are looking at how can they solve some of the processing bottlenecks. Do they use GPUs? Do they use hardware accelerators? And of course, the same timing issues affect the ODU as well that we just talked about on the ORU side. Now, the ODU also has to be hosted on virtual appliances in addition to physical appliances. And finally, on the OCU side, the challenges are different. What we are seeing is scalability. How many DUs can each CU support? What's the total number of UEs you can support? And this goes to tens of thousands. And what is the total throughput that we're talking about? You can scale all the way up to 100 gigabits per second. On top of that, you're also talking about the separation between the CP and the UP parts of the central unit, the CU-CP and the CU-UP, and this requires coordination over the E1 interface between the two. To get into some more specifics, granted these are early teething problems, but these are generally catastrophic in nature as we get into early interrupts between the DUs and the RUs. The DUs do not proceed if some of the expected protocol options are not available. I gave an example here of the DHCP. Similarly, the M-plane implementation is still in its infancy. In many cases, there are workarounds. And cases where the M-plane is there are parameters that the DU might expect, even though they are optional. If they're not there, then the DU is going to halt. And without the M-plane, there is no CU plane beyond that. The bring-up sequence is another issue where it is clear in the spec. Again, there's a great deal of flexibility involved here. And when you look at it from a CU plane, the DUs are designed with very specific RU capabilities. We already talked about the RU category, whether it's A or B. Typically, only one of them is supported. Also, the beamforming models, there are 4 defined in the specifications. The DU supports 1, and the RU better match that. Also, the compression ranges from 9 bits to 14 bits. This is of the IQ samples. And whatever compression rates you're supporting on the DU side have to be matching on the RU side. So a lot of things have to be aligned between the DU and RU for things to work. Again, these are early teething problems. We expect these to be resolved, but the interop has been challenging at the very beginning. In my final slide for today, I will leave you with how Keysight provides a complete ORAN test solution. To the left, you can see the UE emulation solution, which simulates thousands of UEs over FR1 or FR2 interface towards the ORAN network, going all the way to a 4G or 5G core and to the internet. Next up, you have the RU emulation solution, which emulates the UEs plus the ORU over a fronthaul interface, eCPRI 7.2x interface, testing the ODU. On the reverse, we are simulating the ODU towards ORU. This is a one-of-a-kind unique solution that we have, which takes the best of all Keysight products and folds it into one umbrella called the ORAN Studio. What's done here is the ODU emulators emulates test vectors, which are IQ samples with varying levels of complexity going towards the ORU, and the output of the ORU is an RF signal that is analyzed for various RF properties. We can close on the other side at different points. One, if you don't have the internet, you could get into a layer 4.7 server that we can close the loop with. Or We could close it with a 5G core simulator, which does a wraparound testing of the whole ORAN network. Then we have the ODU and the OCU emulators. So we could close the loop where if you want to just test the ODU, we can have the OCU simulator, which is the F1 interface going towards the ODU. Or if you want to test the OCU, whether it's OCU, CP, or OCU, UP, we could do it using the IXLOAD DU emulation going towards the OCU. We also have a complete solution for testing the EPC and the 5G core using the load core solution, which can test each of these nodes in isolation or as a whole. And lastly, we have the RIG tester that can simulate and test the E2 interface. Before we move on, we would like to take a quick poll. This will let us know if you would like additional follow-up from Keysight. If not, then just please skip the poll question. There are 3 options, as you can see. Now don't forget to click the submit button. Keysight holds many virtual events throughout the year, and we ask that you take a couple of minutes to complete the survey to the right of your screen. Now on to the QA. If you have a question, please enter it in the QA window. We would have time to take a few questions today. Let's see, here's the first question. How do ORAN conformance and interoperability tests complement each other? Okay, so interoperability tests validates that the devices can communicate and understand with each other. So if you talk about the ORU and ODU, it is there to ensure that they can actually work with each other. What it does not do, however, is verify that they are communicating according to the specification. This is where conformance test comes into play. So the purpose of conformance test in that case is to validate that each of these subcomponents, whether it's ODU or ORU, operates according to and is aligned to what is said in the specification. Hope that addresses that question. Yes. The next question is, what is the difference between ORAN and 3GPP standards? Do they overlap with each other? Yeah, so both standards complement each other and both have capabilities and operations in the radio access network. So one standard fills the gaps that's needed for the other. I'll give you an example. 3GPP conformance testing has a strong emphasis on the RF performance of radio units, while the ORAN conformance testing has a strong emphasis on the cross-domain interoperability between the different manufacturers without testing the RF performance. And the reason for this is already defined in the 3GPP conformance test. Next question. Does ORAN support 5G or is it applicable to LTE as well? The standard itself targets LTE, LTE Advanced, and 5G NR. Most of our discussions today was in relation to 5G, but the standards do not preclude from this being applied to LTE. Do you need different ORAN test solutions for FR1 and FR2 radio units? No, the ORAN standards and the solutions are agnostic to whether you are using FR1 or FR2. From a baseband side, it does not differentiate between the two. There are some specific concepts that are applicable or more applicable to one versus the other, but in general, the ORAN solutions do not differentiate between FR1 or FR2. Okay, time for one final question. Does ORAN support advanced concepts such as beamforming and multi-user MIMO? The short answer is yes. Just like traditional base stations, now the disaggregated components are capable of managing beamforming and multi-user MIMO implementations. The standard defines how to do this through signaling between the ORU and the ODU. There are specific section types and section extensions in these messages between the ORU and ODU that carry this kind of information. The exact implementation that the ODU chooses to calculate beam weights and transfer this information back to the RUs and the UEs so they can be in a MU-MIMO situation is quite varied. One of those implementations uses SRS as a mechanism to calculate beam weights. But yeah, this is a topic by itself. Certainly this is something possible, and it is defined in the standards. This concludes today's webinar. As a reminder, you will receive an email when the recording becomes available. Before you leave, you can download a copy of the slides now in the resources widget. Once again, thank you very much for joining us today. This webinar was brought to you by Keysight Technologies. Bye for now.